Hello and welcome to my demo and presentation on the Frontend SvelteKit application for ShutterSpotter. I'll be talking about each column on this table in order from left to right, starting with charts and analytics. 3 chart components have been created and each decorates the Frappe charts component with some additional functionality. I've kept these components as generic as possible so that they could be reused in other parts of the app. The type select chart component allows users to switch chart types using radio button controls, and the chart is re-rendered each time the control changes. It's used here to display the count of locations grouped by their categories. The developer can provide an array of chart types as props to the component, and each chart type will be given as an option to the user. Some default chart types have been provided for this prop. Otherwise, the component takes input data in the same format as a regular Frappe chart and allows developers to provide all additional Frappe chart configuration in an options object. The heat map component shows a GitHub-style heat map that groups data by date. Here it's being used to show user signups. I've made this component simple for developers to use. All they need to do is provide a list of timestrings in ISO 8601 format. These timestrings get converted into the Unix time format expected by Frappe charts before being grouped and counted. Developers can also choose to display only the current month's data and can provide additional Frappe chart options. The last chart component created is what I've called the time bucket chart. It groups and counts times by day, hour or month, and users can specify the time range of data to display. A trend line can be displayed to show the trend in data for the range of time specified. A linear regression algorithm is used to calculate the values for this trend line. Users can also choose to show a projection for this chart, which extends the trend line into the future, and the range of projection can also be specified. I'll show now some of the key features of this component. Similar to the heat map component, it takes an array of timestrings in ISO 8601 format as input. Values can also be provided for the initial count of buckets, bucket size, display label, as well as options for displaying trend lines and projections. The trend lines are calculated using a simple linear regression algorithm. The x and y values of the data in the time range specified are passed to a function to create a linear regression model, which consists of a slope value, which is effectively a multiplier for any given value of x, and a y-intercept value, which is a constant number added to each resulting multiplication. The getY function does this when provided with a value x and the model. I'll now show some of the mapping and weather components used in the app. After logging in, a user is redirected to their dashboard, where a prominent map is displayed showing all their locations. Users can filter the location markers by location category. Overlays can be added to the map that display the current weather conditions, including clouds, precipitation, pressure, wind, and temperature. Clicking on a marker shows a pop-up that displays the location's name, which links to the locations page. On this page, we can see some more detailed weather conditions for the location, as well as another map. Below the main dashboard map, a list of all the user's locations is displayed, each of which includes a smaller map that doesn't include any of the overlay or filtering options that the larger map does. I'll now add a new location using the form at the bottom of the page. I'll also take the opportunity to demonstrate the sanitization the backend of the app provides with the disinfect package. I'll do this by adding a script element to the location's description. After the location is created, it is added to the list of locations, and we can see that the script element has been removed. A marker for the location is also added to the map, and the map centers on this marker. Looking at the code now, I've tried to keep the leaflet map component flexible. Props can be provided to specify whether or not to show the map's zoom or layer controls, and the HTML ID of the div the map component will be displayed in, as well as its class and style attributes. A Svelte store called latest map marker can be provided to the component, and if it is, the component will subscribe to it and update the map's markers with the new value if its value changes. Overlay objects can also be passed to the map, which allow map overlays such as those for weather conditions to be added to the map. I'll now demonstrate some of the image features of the app. On each location's page, a photo gallery with all of the photos for that location is displayed. This photo gallery is responsive and reorders the photo columns when the page size changes. Hovering over an image enlarges it slightly and also makes the image less opaque. Clicking on an image darkens the background and shows a modal containing the enlarged image, as well as additional photo info including its title, description, and the tags for the photo. Clicking the delete button in the modal closes the modal and deletes the image from the database, file server, and also the page's photo gallery. Photos can be added using the form at the bottom of the page. I'll also make use of some serverless features to add a watermark to the image, sharpen it, and convert it to grayscale. After being created, the photo is added to the page's photo gallery, and we can see how the serverless function has processed the image and a watermark has been added. Now looking at some of the code for this, the photo gallery component makes use of the Svelte simple modal component, as well as a more generic image gallery component, which I have created based on the Svelte image gallery component. The photo gallery takes an array of photos and an optional latest photo store writable as props. It converts the photos into the format required for the image gallery and sets up subscriptions to listen for added or deleted photos. These subscriptions update the photos array, which in turn causes the images array and the image gallery to be updated. The photo modal display is also managed using a store called photo modal. The event emitters onClick from the image gallery component and onClose from the modal component itself cause this store to be set with either an instance of a photo modal component containing the clicked photo or null. The modal component listens for changes to this store and either displays or closes itself based on each value received. The serverless function for processing uploaded images is contained in the netlify/functions directory. Its handler takes an event whose body contains the base64 encoded raw image. The Node.js library Sharp is then used to perform various image processing functions on the image before re-encoding and returning it. A JWT-based auth flow is used in the app. When the backend successfully authenticates a user, either using their email and password or GitHub's OAuth flow, a JWT is set containing the user's ID, email, and authorization scopes, which have been used to control access to certain API routes on the backend. This JWT is then returned to the client and attached as an authorization header on all future API calls to the backend. We can also see here that the bcrypt library has been used for hashing and salting passwords. Hashing happens in the addUser method of the user store, and we can see here an example of a hashed password stored in the database. The bcrypt.compare method is used in the authentication user API to compare the plaintext password provided at login to the hash password stored in the database. We saw earlier how sanitization of potentially malicious HTML and JavaScript was carried out. Happy's Disinfect plugin has been used to achieve this by cleaning queries, params, and payloads on all routes. OAuth has been configured for the app using GitHub's web application flow. Users can sign up for ShutterSpotter using GitHub, which prompts them to authenticate with GitHub. Upon successful authentication, GitHub redirects to its /signup/GitHub route on the Frontend app and sends a short-lived single-use code. The Frontend app then sends this code to the backend, where it is used with the client ID and a client secret to obtain a token from GitHub. This token is then used to access the user's GitHub profile information, and finally a ShutterSpotter user is created using unique identifiers contained within it. A similar flow is used for logging in with GitHub, except a different redirect endpoint is used, and the backend uses the GitHub profile information to retrieve the user from the ShutterSpotter database and then set a JWT. From there on in, the standard JWT-based auth flow is used. We can also see that the backend app has been used to set the user's avatar using GitHub profile data. The front-end application has been developed using Gitflow, and the branches and releases can be seen on its GitHub repo. The backend for the app has been deployed in Render, and the front-end and serverless functions are deployed on Netlify. TypeScript has been used throughout the project on the front-end and back-end. That's it for this demonstration. Thank you for watching.